So I'm Longfei. I'm a PhD student at Yale University, and I'm presenting LiDO, which is a novel model of Byzantine consensus protocols that supports proving both safety and liveness of these protocols through refinement. And this is joint work with Yoonseung Kim, Ji-Yong Shin, Jieung Kim of Honoré, under advisor Professor Zhong Shao. So for some background of our work, I will begin from an introduction of Byzantine consensus protocols. A consensus protocol is an algorithm that makes a group of networking nodes behave as if they were a single atomic state machine. Of course, any networking system cannot be truly atomic, since you always have latency between submitting requests and receiving result. And so the correctness condition is defined by the well-known concept of linearizability, which says any network trace is linearizable to an atomic state machine. And so it's also called a state machine replication algorithm, or SMR. Now, beyond safety, of course, we also expect the protocol to satisfy liveness, which means that if a client submits a command, then it's eventually executed. And finally, we expect the protocol to tolerate a subset of Byzantine faults, meaning when the nodes are faulty, they can send out any possible message. And that contrasts with benign faults, where if the faulty nodes do nothing. So any networking system relies on message delivery to get progress. And so we need to consider different models of communication. In an asynchronous model, there is no guarantee on the of message delivery. They can take arbitrary time to arrive. While in synchronous networks, the assumption is that there is a known bound delta on message latency. However, both these models are not very realistic. And so the most important class of protocols work under the partial synchrony assumption, which says there is a unknown time point called the GST. Before GST, there is no guarantee on the message delivery latency. But after GST, there is a known bound delta on the latency. And in this work, we mostly consider consensus protocols under the partial synchrony assumption. So in the literature, there are a very large number of consensus protocols that has been proposed, and a very large number of them work. They follow a very general paradigm called the round plus pacemaker structure. In these protocols, the protocol is structured as an infinite sequence of smaller protocols called rounds, and each node only participates in one round at a time. And if all the nodes are in the same round and the leader of the round is non-faulty, then it's guaranteed that it can make progress in the system. However, as we all know, the nodes could be faulty, and so when the leader of a round becomes faulty, there is a mechanism called the pacemaker that kicks in and moves the system to the next round. Now, here is a very simple description of the pacemaker. You just observe whether there is progress in the current round. If you don't observe any progress, you broadcast a message called the timeout. And if you collect a sufficient number of timeouts, you enter the next round. It sounds very simple, right? However, it turns out this very simple implementation of the pacemaker does not satisfy liveness unless we make additional assumptions on the network. To make it actually work, you need additional tricks. And here you can see several different ways to make it actually live. And the red part shows you the difference between these versions. But you can see that they have very subtly different liveness properties, which is why these Byzantine consensus protocols are very difficult to implement correctly. Now, in the literature, there already exist many existing works that analyze the safety or liveness of these protocols. But so far, we haven't seen any general framework for proving both safety and liveness of these protocols. And this leads us to our contribution, which is called the LiDO model, which we claim supports proving both safety and liveness of these protocols through refinement. So this figure shows you the structure of our safety proof, which takes the form of layered refinement. At the very top level, you can see there is the SMR interface where the clients submit requests and receive responses. At a slightly lower level, the clients send the requests to individual proposers in the system, and the proposers are coordinated by an abstract pacemaker. Roughly speaking, the proposers execute the requests by following 4 steps. First, it needs to get the consensus log, and then it appends the method to the log. And finally, it commits the changes to the log. And if all these procedures succeed, then it passes the control to the leader of the next round. Now, of course, the proposer could be faulty, and so it needs to work with a group of voters to ensure correctness. And the voters are implemented by running an infinite loop of receiving requests from the leader and checking if it's safe to vote, and if yes, then it sends the vote, otherwise it drops the request. And finally, at the lowest level, we have the network model where these proposers and voters are implemented on individual networking nodes. We also support proving liveness by refinement. We observe that in many of these SMR protocols, liveness reasoning follows also a very general pattern where the pacemaker allocates a fixed amount of time to each round. And within each round, it's divided into several events, including making the leader enter the round and then executing a number of phases. And if each phase succeeds, it's guaranteed to commit at least one method. So to summarize, our contribution is a LiDO model, which is a pacemaker-aware model of partially synchronous SMR protocols. And we also obtained safety and liveness proofs for a modern Byzantine consensus protocol called Jolteon, based on our LiDO model. And in the following slides, I will first introduce the LiDO model and then show some details of the Jolteon implementation. But I will skip a lot of details due to limited time, but you can find them in our paper. So the LiDO model is based upon our previous work on a model called the atomic distributed object, called ADO, where we used it to implement several benign consensus protocols and verified their safety but not liveness. The core idea of ADO is that we use a cache tree-based abstraction for the consensus log, and model the growth of the log through 3 steps, which we call pull, invoke, and push. And we represent the results through these figures called cache nodes. Now, the ADO model was successful for benign protocols, but when we apply it to the liveness of Byzantine protocols, we immediately encounter several problems. The first, of course, is that it's an atomic model, but and to say that a protocol refines the model, we reorder the network events, but in reordering events, we destroy the temporal properties. And so we reformulated ADO as a concurrent but linearizable object. The second issue, of course, is that it lacks information about the pacemaker, without which, as we have seen, we cannot do any liveness reasoning. A solution, of course, is we augment the ADO model with an abstract pacemaker state. And this leads us to the LiDO model, which is summarized in this figure. On the top part, we still have the ADO cache tree, which are controlled by the pull, invoke, and push operations. In the bottom part, we have this start next and elapse operations, which represent an abstract timer. So start next represents the operation where the leader passes control to the next round, But if the leader does not cause it, then the pacemaker comes in and calls timeout start next to start the next round. So to see how this works in practice, I will show an example trace of LiDO. So on the top right part, we see the pacemaker state, which consists of round and remaining time. In the bottom part, we have the cache tree, which initially contains only a single node called the root node. And on the top left part, we see the committed consensus log, which shows how LiDO refines SMR. So let's assume that GST does not occur until the third round. So in the first two rounds, the operations may or may not succeed. So in the first round, the leader comes in and first calls pull, which is to get the up-to-date cache log. Of course, it only obtains an empty log since there's nothing before the first round. Then it proposes its own method, let's say method A. That's the only method in the log right now. Now, it tries to commit this method A, but say due to network failure or not enough time, it fails, and this results in a T cache. So the pacemaker comes in and starts the second round. In the second round, fortunately, the leader sees the method proposed by the first leader, and so this E cache is drawn from the first M cache. Then the second leader appends its own method, let's say method B, and attempts to commit the log. Unfortunately, it fails as well, resulting in the T cache shown here. Now the third round begins. The leader sees only method A by the first leader, but not the method B. It appends its own method C, and it attempts to commit the log. This time, since it's after GST, well, it succeeds. And at this point, the method A and C are committed, so you can see it on the top left part, the committed consensus log. So this shows that LiDO defines a transition system which captures both the state of the consensus log and the pacemaker. And we now look at how we can prove liveness of SMR protocols using this model. So our first observation is that in general, we only care about non-Zeno traces of systems, which means that in any finite period, there can be only a finite number of events. And this inspires us to represent an infinite network trace in the following way. We will just divide. We start from the GST time point and then divide the time by periods of delta. So here at GST, the trace is tau 0, and then by the time GST plus delta, we have the trace tau 1, and so on. And what this gives us is that we can easily state the liveness assumptions as safety properties on each period. For example, to represent the partial synchrony assumption, we will just say, if you send a message before the beginning of a period of delta, it's delivered at least once before the end of the period. And with this, we can summarize our liveness proof in 3 simple steps. First, we formulate a set of safety conditions on the segmented traces of LiDO. Then we prove that under these conditions, we can commit new methods infinitely often. And finally, we just show that all the live network traces refine all the live traces of LiDO. Which implies that at network level, you also commit new methods infinitely often. So we applied our methodology to a Byzantine consensus protocol called Jolteon. It's a two-phase protocol that's also been deployed in the industry. And the figure below shows how our implementation model works. It's a main process with a timer attached, and the main process has handlers for external request messages and timer signals. These handlers can then be extracted to OCaml code, which makes it an executable implementation. This figure summarizes our proof effort. So as you can see, the safety proof took only around 4,000 lines. And the liveness proof took around 1,700 lines, which shows that our methodology is a very efficient way to prove safety and liveness of SMR protocols. We also mentioned that in recent protocol design literature, there is an important optimization called pipelining. It reduces the best case latency of these protocols, but it also decreases its worst case latency. It's slightly more difficult to verify because pipelining depends on cooperation between consecutive leaders. Nevertheless, our LiDO model applies to these protocols as well, and we obtained safety and liveness of pipelined Jolteon. So to conclude, we introduced LiDO, which is a model of consensus protocols supporting both safety and liveness refinement. And we believe it's the first mechanized safety and liveness proof for a pipelined Byzantine consensus protocol. We also mentioned that our work leaves a lot of ends open. For example, we only considered partially synchronous consensus protocols with a fixed set of participants. But in the blockchain industry, we also need other kinds of protocols, for example, asynchronous protocols or protocols that support open membership. And handling these kinds of protocols are work for the future. And again, I'm skipping a lot of details due to limited time, but you can find all those details in our technical report and artifact, which is available on our website. That's all. Thank you.
We have time for a quick. We have time for a quick question.